In 1666, a guy named Sir Isaac Newton has made a discovery, a magnificent discovery which called Newton's law of motion. Together with that discovery, alongside with some other discovery that made throughout the centuries, such like Pascal principle and Bernoulli's principle. So people thought that they have achieved the highest level of physics. Newton's law of motion consists of the first law, the second law, and the third law. Together with the laws and the other discoveries at the time, people at that era thought that as the discoveries seems like beyond of their time, they thought that they have solved everything. There is a time when the classical physics is the mainstream in science, and the people also thought that there will be no more other physics discoveries, as they thought that the existing theories can describe almost everything. But it only lasted until the 19th century, when at that time some scientists had done some research that proved slowly and but surely that the classical physics are wrong. For example, Gustav Kirchhoff in 1859, who discovered black body, and Niels Bohr, who just invented his first quantum hydrogen model in 1888. Since then, quantum physics, or much known as modern physics, had replaced classical physics in terms of atomic level physics. Why I'm saying this, I'll explain it later. But what I want to say now is one of the major components that leads to this discovery of modern physics is called particle wave duality. Wave particle duality is a concept that explains why some particles at atomic level such as light and electron can behave both either like a particle or either like a wave. When we talk about wave, let's say light. Some of us will already know that light often acts as a wave, which can be proved with Young's double slit experiment, which my grandpa can explain further about that.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this. Two bands of hits. And with waves, we get an interference pattern of many bands. Good so far.
And that strongly proves that light can behave as a wave. But there is another phenomenon that makes scientists a little bit confused, which is photoelectric effect, which is when a light strikes on the metal surface, it will the valence electron of the atom at the metal surface will absorb the energy from the light, and the electrons will be ejected out from the metal surface. And this is what photoelectric effect looks like. Yo, Ravina, wake up!
Yeah.
In the last video, the knock on the door resembles the light that strikes the metal surface, and the door and the coil itself resembles the electron at the metal surface. But now, what I want to emphasize is, in classical physics, light travel in a wave with the energy evenly distributed throughout the wave. So, classical physics expects that if a very dim light with low energy level of light strikes the metal surface, the electrons and the atoms of the metal surface will take some time to build up the energy to collect some more, and then pop, eject out from the electron from the metal surface.
Two hours later.
Can you talk a bit louder next time? I can't hear you.
But that's wrong. It doesn't work like that, because dimmer light means fewer photons ejected at a time, not lower energy level. So, when a single photon has enough energy to eject the electron out of the metal surface, the electron will be ejected immediately, no matter what. Don't believe me? Scientific experiments prove that. Davina? Oh, Davina!
Yeah.
And this shows that light cannot always behave like a wave, but sometimes like a particle. So, we can conclude that particles like light or electrons cannot be 100% wave or 100% particle. But I can say that it's a combination between a wave and a particle, or which scientists call photon. Light behaves as a wave if you want to know how it travels from one place to another, from one point to another point, and how it travels through matter and so on. But at the same time, light can also behave as a particle. If you want to know how we react with matter, for example, what will happen if light struck an electron in a metal surface, just like we said before. So, we can conclude that particles like light and electron and whatsoever experience wave-particle duality, which means a particle can exhibit both wave and particle nature but never be both at the same time. If you want to knock down someone, break through something, or maybe slapping someone, you need a momentum. Momentum, defined by Newton, is mass times velocity. But how can a photon which has no mass, so 0 times velocity, any velocity will be 0? How can a photon which has no mass can knock down electron from the atom? So this is what's the confusing part. Einstein used his theory of relativity to relate the momentum with wavelength. What? Which we can deduce a new formula, which is P equals to h over lambda. The smaller the lambda, the larger the momentum.
Bruh.
In 1923, Louis de Broglie of France has a mad idea. He proposed that if an atomic scale particles like light and an electron can exhibit wave-particle duality, maybe everything in this world can do the same, can act as a wave and as a particle. Wow, that's interesting. How can a baseball, an elephant, or even our human body act as a wave? Lavender, can you come? De Broglie rewrite the Einstein's equation by substituting the momentum P with mv, which we can get mass with the massive object. So we get the new formula, which is lambda is h over mv. The h at the top is the trademark of the modern physics, which what we call Planck constant, and this value is like 6.63 times 10 to the power of negative 34 joules second. It's just so tiny, you know. It's so tiny that even if we evaluate it with the baseball, the wavelength will be just 10 to the power of negative 35. So small, you can't even notice it. Or even our body. If the Broglie wavelength legitimately applied in a massive object, for example, we have Davinder here. Hi Davinder.
Hi.
May I ask you, what's your mass?
74 kilogram.
Okay, 74 kilogram, is it? Okay. What's your average velocity when you walk upstairs?
I assume it's 0.8 meter per second.
Meter per second, yeah? Okay. Right unit. So now we get this wavelength. Even the atom is bigger than this. Yo, Davinder, come here a bit. Electron has mass, a tiny mass, and this size is also tiny. But its de Broglie's wavelength is also tiny. So, that de Broglie wavelength is reasonable and significant for the electron. So, we can conclude that this theorem can be accepted. Conclusion: after numerous experiments have been done and been proven true, and some theories after theories after theories, so without a doubt, we can conclude that every object in the atomic scale exhibits wave-particle duality. In fact, every massive object like this table, even myself, even the chair, even the recording phone also exhibits wave-particle duality, but it just isn't noticeable as the wavelength and the effects are like negligible. But what if they do?
NANI?!
Hey, both of you! Hey Davinder, I'm calling you too.
Really?
God damn, the ball is traveling like a wave. Which direction should I dive? I think I just guess it.